In this video, we're going to talk about a concept of category theory which is very important and which has close connections to some concepts we've already seen, such as naturality conditions, as well as some concepts that we'll cover in future videos, such as adjoint functors. So we're going to read through the definition at the bottom first, but it's important to remember that a lot of times in category theory, definitions are really just summing up a certain pattern, and a lot of times those patterns can be better captured as graphics or diagrams like this. So rather than trying to memorize sort of very terse definitions, such as the one on the bottom, it's often a lot more helpful to try to memorize these patterns as graphics, and then you can just write out the definition anytime you need to apply it because you remember what the pattern is. You may need to remind yourself as you write it out and draw the pattern out to write it out, but once you have it, you should be able to write out the definition based on what you see in the graphic. So let's read through it once all, and then we'll look at how this graphic captures that definition. Suppose we have two categories, C and D, and suppose we have some functor f going from D into C, then universality will apply to a certain pair where the first element in the pair is an object, which we will call U, in the category D. We find U over here. And the second element of the pair is a morphism U subscript C, where U subscript C goes from some fixed object C in C to the image of U under our functor F. So UC goes from C into F of U. And what it means for that pair to be universal is that for any object D in D, if we have some morphism F going from C into the image of D under F, so for any morphism F from C into F of D, there is a unique morphism tau F in the category D, such that the image of that morphism allows this diagram here to commute. That is, f of tau of little f after UC is the same as f. So in some sense, what you're saying is that any morphism going from C into any object in the image of the functor f can be, in a certain sense, factored through this morphism UC. Note here that our universal morphism, as we'll call it, UC, depends both on the fixed object C in C, as well as the functor f, because it needs to know what f maps U to. So we say that this pair, UC, is universal for the pair C and f, the functor. So notice here that just like in every there exists a unique type of conditions, we're actually saying two things at once. It sort of looks like one statement, but there's actually two pieces of information that we're getting. One is that for any morphism f going from C into any f of D, there is a morphism that makes this commute. So we may not know whether there's a morphism from f of U to f of D that makes this chain commute or not. But in this case, we're saying we know that there is one that makes this commute. And on top of that, the second piece of information is that there's only a single morphism in D that maps to that special morphism that makes that chain commute. So let's take a look at a couple of examples of universality, because oftentimes definitions in mathematics make a lot more sense once we've seen them applied to something. And so the simplest possible functor, arguably, would just be the identity functor on the category of sets. So let's try applying this definition of universality to the identity functor from set to set. So what would it mean for a pair UC to be universal for C and the identity functor on set? That is the functor going from the category of sets to the category of sets, which just sends every set to itself and every set function to itself. Well, in this case, both C and D are both the category of sets, which means that C is going to be a set and U is going to be a set. So that means this pair is a set together with a set function, which goes from C into f of U. But f of U is just U because this is the identity functor. So UC goes from C to U. And if this pair is universal, then what that means is for all D and D, that is for any set D, and for any set function which goes from C to f of D, which is just D because this is the identity functor. So for any set function from C into D, there has to be a unique set function going from, which we call tau of f, which goes from U into D, such that, well, f of tau of f is just tau of f because this is the identity functor. After U of C is f. But remember that we said that there exists a unique tau of f, was actually two properties packed into one. And so the first one we said was an existence condition, which said that for any set function f from C into any D, we must be able to find a set function tau of f, which makes this equal, or which makes the diagram commute. But that means that UC has to be injective. Because otherwise, suppose we had C with two elements, U with two elements, and D with two elements. Well, if UC was not injective and say mapped both of these elements to this element here, then anytime that F mapped these two elements to different elements in D, we would no longer be able to replicate that because these two elements have collapsed by UC here into the same element, and so they both must map to the same element in D by tau of F. But that's not the case. We need this to be able to happen for any F, including ones where they send them to different elements. So it must be the case that UC is injective. But the second property, which is that tau of F is unique, means that this must be also surjective. Because if not, then see how, again, our UC is not surjective here. There's an element that's not being mapped to. Well, then we could just change what this element was mapping to get a bunch of different tau of F's. And that would not affect this formula at all because this element is leaving out the element that causes the problem here. So this equation is going to hold every time, even though there's a whole bunch of distinct tau of F's. And so this uniqueness property fails. So what we actually have here is that if this pair is universal, then UC has to be a bijection. But conversely then, take UC to be any arbitrary bijection, then it's an isomorphism in the category of sets, which means there is some UC inverse, And then if f is any arbitrary function going from C to D, then we can just set tau of f to be equal to f after UC inverse, which will of course give us tau of f after UC is equal to f. So we can always find a tau of f to make this property true, to make the diagram commute. And moreover, this inverse is always unique. So this composed morphism is also unique. And so we have this property satisfied, which means that we've actually proved that the pair UUC is universal if and only if UC is a bijection. Let's look at another example of universality in a slightly different context, which is linear algebra and vector spaces. So this example is, in my opinion, one of the more intuitive examples. And in order to set this up, let's recall a fact from linear algebra, which is that if B is some basis for a vector space V, where V is in the category of vector spaces over K, where we've fixed K is any arbitrary field, then any mapping which maps the basis vectors of V into another vector space W uniquely determines a linear transformation T from V to W, where the linear transformation agrees with that f function on every basis vector of V. So I'm just going to take this statement as given, but a good exercise would be to go back and review this linear algebra proof. It's not too difficult. So what you need to do is you need to prove that if you give me any f, which is mapping the basis vectors B of a vector space V into another vector space W, then basically there is always a linear transformation going from V to W that agrees with f on all of the basis vectors. And not only that, but it's unique. So there's only a unique linear transformation that satisfies that property. If you need a little bit of a hint for that one, notice that if we take any vector V in the vector space V, then we can express V as a linear combination of those basis vectors. And then basically what you do is you just define T of V to be the coefficients for each of these basis vectors, just applied to whatever we mapped the basis vectors to in W. So C1W1 plus C2W2, where WI is equal to basically just whatever F maps VI into for all VI in B. So we've invented this mapping T from V to W. So in order to complete the proof of this statement, what you would need to do is that you would need to show first that this is a proper linear transformation, that it satisfies the properties of a linear transformation, and we'd also have to prove that it's unique. So there is only one linear transformation that satisfies this property. So you can use that as a bit of a hint to finish this exercise. So let's draw this situation out to understand it a little bit better. So if we have our basis vectors B and some mapping F into a vector space W over a field K that we've fixed, well then F is a set function because B is not a vector space, it's just a set of vectors. So This lives in the category of sets. And we're basically saying that anytime you give an f which maps the basis vectors of B into a vector space W, then that determines a unique linear transformation, which we might call T of f, from V into W. And not only that, but that linear transformation agrees with all of the mappings of all of these vectors by f. So what that's saying basically is that if I include the basis vectors B into themselves in the vector space V, that is, if I use the inclusion map from these basis vectors, which just map to themselves within the vector space V, then what I'm effectively saying is that applying T of f after applying the inclusion map is going to be the same thing as f, right? F sends the basis vectors of B to certain elements of W, and we need for this linear transformation to agree with all of those mappings. So that means if we include these vectors into V with themselves, then they need to map to W in the exact same way. And that can be expressed by this equation. So how can we somehow capture the uniqueness property within this diagram? So we said that for any f, there's a unique linear transformation T of f. Well, what we could say is that we know that T of f has to exist over here in vect k because it's a linear transformation from V to W. So we know that T of f lives over here. And we know that there's a forgetful functor, which we might call f, going from vect k into the category of sets, which just maps every vector space to itself and every linear transformation to itself as a set function. But then, if there's only a unique way for T of f to be determined to make this equation work, then of course there's also only a single T of f that gets mapped by the forgetful functor into T of f, namely of course itself, because ft of f is just T of f because it maps everything to itself. So notice that we've actually shown exactly the universality property here. We have, for any mapping f from B into W, a single linear transformation in vect k going from V to W, which we might call T of f, such that when we map it by the forgetful functor to itself, of course, it's the only one that makes this diagram commute where this is the inclusion map, where B maps itself, every vector to itself in the vector space V. So what we can say is that this property is actually exactly equivalent to a universality property for the forgetful functor. So let's write it out in full. So suppose B is a basis for a vector space V in vect K, then for any vector space W in vect K, and for any mapping F from those basis vectors to that vector space W, we have that there must be a unique linear transformation T of F going from V into W such that we have that T of F after I is equal to F, where I is the inclusion map. So we'll write that there. This is the inclusion from B into V, where everything just maps to itself. And since we have the forgetful functor f, where t of f is just going to map to itself, we know that we can add this f in front and this equation will still be satisfied. And so this is exactly the property that we have here. We're stating it in exactly the same terms. So what can we conclude then? We can conclude finally that the pair V and the inclusion map from B into V is universal for the basis vectors B and the forgetful functor F. So we've proved this result, and this to me is a pretty intuitive and direct application of universality to the context of linear algebra. And so we can see that universality allows us to compress a lot of information into a fairly compact statement, right? That we have this big long statement up here, which can be reduced just to this once we have the machinery of universality from category theory in place. So now that we know that there's a universal pair corresponding to the forgetful functor from the category of vector spaces into the category of sets, let's see if we can find one for the same forgetful functor, but this time going from groups into sets. So here we have the functor f, which is the forgetful functor, which sends every group to itself as a set, and every group homomorphism to itself as a set function. So let's apply the definition of the universal pair down here. So in this case, if a pair U and UX, which is a set function going from X into U, is universal, for, in this case, X and the forgetful functor F, then for any group G and for any set function F going from X into G as a set function, there exists a unique TF, tau of F, where tau of F is in the category of groups over here. So what does it have to be? Well, it's a morphism in the category of groups, so it has to be a group homomorphism such that this diagram commutes. That is tau F after UX is equal to F. And of course, in reality, we should have our F of T, tau of F here. But again, this is just the forgetful functor, so it's just going to send tau of F to itself as a set function. So we can just get rid of it and just consider these as set functions. So remember, in the case with the vector spaces, this universal morphism here, UX, was actually an inclusion map from the basis of the vector space V into V. So I wonder if we could somehow use an inclusion map here as another type of universal morphism for this forgetful functor instead. So what would that mean? Well, that would mean that X would have to be a subset of U, because if we have an inclusion map going from X into U, that means that X is just picking itself out. Each element of X is just picking itself out in U, which means that all of the elements of X must also be in U. That is, X is a subset of U. So based on that discussion, let's try reapplying this definition with here, instead of some arbitrary function, we have the inclusion map from X to U. So first, let X be a subset of U, so every element of X is in the group U. Then U and the inclusion map from X into U is universal for XF, where F is the forgetful functor going from group into set. Well, we see that for any group G and for any morphism F from X to G, we need to have a single group homomorphism, tau of F, such that this commutes. But we just saw a very similar situation with the vector space example, where we were commuting with the inclusion map here. And what did we say? Well, we said that what that meant was that any mapping F going from X into G uniquely determines a group homomorphism that this time. Last time it was a linear map, but in this case it uniquely determines a group homomorphism, tau of F, from U into G, such that it agrees with F for every element X. So basically, when tau of F maps any of the elements of X, it has to be the same as when F maps any of the elements of X, and this is for all X in X. When this is the case, when tau of F agrees with F on all of the elements in some subset, then we call tau of F an extension of F, because tau of F is doing the same thing that F is doing for all of the elements of X, and then for all of the elements in U that aren't in X, it can do something else. But this property here actually has a name from group theory. We call it the unique extension property. So if some group U has some subset X, and we have the case that for any mapping X into any group G, then there's only one homomorphism going from U to G where all of the elements of X are mapped the same way as they are by F, then we can say that U has the unique extension property with respect to its subset X. So then we can replace the condition at the bottom, and we can say that if X is a subset of some group U, then the group U and the inclusion map from X into U is universal for X and the forgetful functor F if U has the unique extension property with respect to X. But from group theory, we actually know that there always is a group that has the unique extension property, and that group is the free group. So in this case, it would be the free group on X, sometimes denoted as Fx. So this free group on X, or sometimes known as the group freely generated by X, is defined to have this unique extension property with respect to X, but we can actually also show it constructively. So if we take A to be the alphabet consisting of X together with the inverse of X, where basically we just have a set X to the -1, where we just have all of the inverse group elements of X, and we consider them as letters in some alphabet, then the set of all reduced words over A actually defines a group, and that group has the unique extension property with respect to X. So if we take every element x as a letter in the alphabet, every inverse of x as a letter in the alphabet, and then we can do certain rules such as applying an element next to its inverse to reduce words from more complex, longer words to shorter words. And the set of all those reduced words over that alphabet, x union x inverse, actually is the constructive version of the free group. And I will link a paper in the description which can prove to you why this exact construction has this unique extension property that we're looking for. Now, if you notice how similar this pattern is to the last example with the vector spaces, you notice that x here plays the part of the set of basis vectors, the basis b, and we actually can call x a basis for the free group f of x. So obviously we don't usually think of groups as having bases, but if you have a free group over x, then you can actually call x a basis for that group. So, with that sort of abstract similarity in mind, let's just summarize all of the universal properties that we've found. So, we said that for any set C, we get that the set U and the mapping UC from C into U is universal for C and the identity functor on set if and only if UC is a bijective function. So that was the first result we saw. The second result was that for any basis B of a vector space V in vect K, where we've fixed some field K, we get that V and the inclusion map from that basis into the vector space V is going to be universal for the basis B and the forgetful functor F, which goes from vect K into the category of sets. And finally, we said that for any set X, the free group F, which can either be defined categorically or constructively, and the inclusion map from X into the free group on X is universal for X and the forgetful functor again, but this time going from groups into the category of sets.